Hello. So we are wrapping up our 10.1 lesson tonight, and we are continuing on with cubic modeling. So remember that our last unit was all about quadratic modeling. So there's going to be a lot of similarities between what we learned last unit in regards to making an equation that represents a quadratic, as there will be towards making an equation that represents a cubic. They are both polynomials. They have similar patterns and behaviors. So there's going to be a lot of things that are the same. So instead of repeating similar ideas and similar processes that we've already learned and hopefully mastered in our last unit, what we're doing is we're just kind of explaining how this might look in a cubic. So for the sake of keeping these videos shorter, trying to do less examples of all of the different things that you could see. What we are going to do is talk about, we're going to make an equation based off of a partially completed equation here with example 3. And example 4, we're going to do a modeling including volume. So we did modeling with quadratics involving area. Now we're going to talk about how does that transfer over to volume. A few things that we don't cover in this lesson that will be required to be known in regards to making a cubic model is the plugging in points to make a system of equations. Remember from our first lesson that we talked about the breakdown of our unknowns, that we have 4 unknowns. Now it's A, B, C, and D because we have an extra term that is an x cubed now. So if we wanted to solve for those 4 unknowns, we would need 4 distinct separate points in order to make 4 distinct separate equations in order to solve for those 4 unknowns. So that's something that we don't cover in this lesson tonight. That is definitely a requirement or needed to be known or could be used with cubic modeling. So just keep that in mind. But it's going to be the same process of plugging in points to make 4 different equations, and then you would just use your calculator to solve for that system of equations. Okay. Example 3. The maximum theoretical power that can be generated by a wind turbine can be modeled by the function boom. Now, I know it looks like AdV might be one big variable, but it says here the P is power, A is the area swept by the turbine blades, D is the density in the air, and V is the wind speed. So take a second and ground yourself in this problem, as we always do when we start a new problem, is just envision what's going on. We're talking about a wind turbine and the amount of power that a wind turbine can create. Now, all of that depends on a couple different things: the area of the space that it's covering, right? So the swept area is the space that it's moving around, right? So if it's a bigger area that it's covering, it's probably going to generate more power because it's using more energy. Versus if it's not covering a very large space, it's probably going to generate less power. So that's kind of the idea of grounding yourself in the problem, right? D is then air density. If we have really thick air because of humidity being by sea level, or if we have really thin air, the amount of energy that is created by a wind turbine is going to be different because it's talking about all of the energy required in order to move that turbine. So the more energy required, the more energy is or power is created. So in a dense air with a place that has really dense air, you're creating more energy because it takes more energy to move through the thickness of the air. And then if you have wind speed, there's going to be that implied in your ability for your turbine to create power. So this moment of like, oh, interesting. Okay, so when I have a wind turbine, I have to think about things like how big, how much area are the blades covering, how thick is the air, and what's the speed of the air that's going on around me in order to know how much power is created. Oh, okay, so all those play a part in power generated. That's it. Just the simple process of being like, what does this mean in the real world? Can I envision a wind turbine and generate an idea of what it all means will be helpful for your problem solving through this. So it then says a certain wind turbine has swept area of 80. Oh, we talked about that before. We said, oh, it depends on how much area it is. And so that's 80. And so A is the area swept, and that's 80. Okay. And it's located at sea level where the air density is 1.225 kilograms per meter cubed. Okay, well, that's then this guy. It says find the cubic model for this wind turbine. So I just turned this guy, A, into a number, and then I just turned D here into a number, and the only input I have left is V, which is good. I only want one input when I have an equation. So all you need to do for this guy is plug in the numbers that you have been given. So P equals 0.297 times A, which is 80, times D, which is 1.225, times V cubed. Just plugging those in. We're going to multiply all three of those numbers together, and we're going to get the final equation of what? When we multiply those three numbers together, we get 29.106. And then V cubed stays, which is fine, right? We can rename this instead of just P. This is the equation or the function of P for P of V. That is all in terms of V, that the function has an input that is the speed, V, only one input. And cubic model because it's raised to the third power. And there you go. You're done. It was just as simple as plugging those numbers in. But understanding how to get there is like the hardest part sometimes. And so just being able to ground yourself is a strategy to use. Okay, use your model to calculate the maximum theoretical power generated when the wind speed is 10 meters per second. Wind speed is V. If that is something that wasn't apparent to you right away, make sure that you're labeling your variables. V equals wind speed. Okay, so then I'm finding P of 10, which all that means is I'm plugging in 10 for V. 10 cubed is 1,000, so then multiplying this by 1,000 just moves the decimal 3 times. So that becomes 29,106. And it says that our power is in watts up here. So then I know that that's 29,106 watts. Given that the wind speed above wind speeds above 20 meters per second are strong enough to cause damage, give a reason why this turbine will not produce more than 300,000 watts. There's a couple ways that you can approach this problem. We've been given two numbers. At the very beginning of your problem, determine where do those numbers go. 20 is wind speed. Okay, so that's V. And then they also gave us power, which is P. So hopefully there's some instinct there of like, well, I should be plugging something in, right? So try that. Try plugging something in. I think the easiest thing to do here is plug in 20. But if your first instinct was to plug in 300,000 for P and then solve for V, you can do so by using the graph and graphing y equals 300,000, right? If we're setting an equation equal to this, y equals to that, then we would have to graph another line to find that intersection. But I think it's easier to just plug in 20. So that's what we're going to do. We're going to find P of 20. Go ahead and find P of 20 on your own. To three significant figures, that's 233,000 watts. So if we cap out at 20 meters per second, because if we have a wind speed higher than that, it's going to cause damage to the turbine. In other words, we don't want to run the turbine if the speed of the wind outside is above 20 meters per second, or else it'll pull the turbines or like rip up something that's going on there. But if it's stronger than that, then we're not running the turbine. Well, if we're running at that speed, this is how much power we earn, which means we won't earn more than that, because if we're running it at a speed above 20, then we would have a broken turbine. And 300,000 is above 233,000. So we won't ever reach 300,000 because it is above our capacity in regards to wind speed. So I want you to take a minute, think about what I just said or re-listen to what I just said, and I would like for you to rephrase on your own, type it in. Why will we never reach or produce more than 300,000 watts? So hopefully you referenced a few things. You referenced the fact that we are limited to be at or below 20 meters per second of a wind speed. And 20 meters per second will only produce 233,000, which is less than the 300,000 that we're talking about. So something along those lines is what we're looking for. It then says determine a reasonable domain for this model. And remember that IB problems tend to build. They tend to reference what happened previously, and we want to build off of what we just talked about. So if it says, hey, a reasonable domain, take a look at what we've just been talking about. Well, we can't have a speed less than 0. So we know that that's a solid domain. That are, we've got domain, and it's V, right? Our input is V, so be careful about that, such that V is going to be greater than or equal to 0. Now we also need to be less than something. We're going to have an upper limit on the wind speed that we can have. And we just talked about the fact that we need to be no more than 20 meters per second. And that is the other end of your domain, is that wind speed must be below or at 20. So one example of creating a model, right? Not the only way we could create a model. There's going to be quite a few other ways that we see that we create models, or we have seen about creating models. But this is one way where we've got multiple inputs, and then it gives us numbers to be like, okay, we can't have that many inputs. We can only have one input. And so what we need to do is we need to replace these values with another value. So we're only using this when the wind turbine has a swept area of 20 and when we're at a place that has an air density of this. So we're only looking at a very specific type of wind turbines that are at sea level, and have that as their area of what the turbines circle around. So it wouldn't work for like Colorado wind turbines. It wouldn't work for Dolomite wind turbines.